Okie dokie. Okay, so here's where we left off last time. We just finished limits, and so now on to derivatives. And really, in a way, this is kind of our first little venture into multivariable derivatives. So it's kind of exciting. And I say sort of. So we did take derivatives of parametric curves, right? But here's two things that we noticed when we were talking about derivatives of parametric curves. One is the definition looks just like the definition of single variable derivatives. There is, in fact, one input variable, right? So it's single input variable, so it's not surprising, I suppose, that the definition that we use is the same. Also, the result, the interpretation that we made of the derivative, it's not slope of a tangent line, but it is the velocity, and there is a point of view on single variable functions. Thinking about that, that gives you position as a function of time as you move along some road or something like that. Where, yeah, in a single variable calculus class, you previously viewed the derivative as representing velocity. So it's not really even all that new in a certain sense. It's different a little bit. But anyway, so with that in mind, it kind of is a single variable derivative. And in a lot of contexts, I'll point out that functions of a single input variable are not even considered multivariable functions. Because the input variable is what matters, right? The output variables, you take derivatives of the output variables one component at a time, whatever. The fact that there's multiple output variables doesn't really add anything fundamentally problematic. Just, one coordinate at a time. So, but the input variables, having multiple input variables is what we don't yet know how to deal with. Parametric curves are not an example of that kind of a problem. So, in a pretty significant way, all that parametric derivatives business is not really multivariable derivatives. So, but now today we're going to talk about multivariable derivatives. Kind of, and again, I'm going to put an asterisk next to it once we've done it in the foreshadowing. Okay, first thing I want to say about multivariable derivatives is there's a bunch of them. It's not like, oh yeah, let me give you the definition of a multivariable derivative and that's it and we're done here, right? No, it's weird that there's actually a bunch of different, fundamentally different kinds of derivatives that have different interpretations and different uses in different contexts. So be prepared, please, for that going forward. You're gonna see a lot of different things. So don't hang your hat on one of them and decide this is what I'm going to, derivative to me is going to mean this one thing and all the others I don't need them. That's not going to fly. Okay. An idea that I want to plant in your head for all of those is that there is a unifying concept. All of the derivatives that we're going to see in this course, they all have this unifying feature that they do what this says. They relate input changes to output changes. Which, it's one of the point of views we had on single variable derivatives, right? Single variable derivatives are a thing, you multiply by dx to get df. Right? And geometrically we think of that in different ways, sure. It has an interpretation in the graph context. It has an interpretation in the car driving along a road context. Different interpretations in different contexts. But in both of those, we're talking about input changes and output changes, right? Rise over the run. What do you multiply by the run to get the rise? Right? That's a relationship between input changes and output changes. Velocity, well, that's distance per unit time. It's what do you multiply by change in time to get change in position. So in all cases that we've seen before, derivatives are relationship between input changes and output changes. And that's what's going to unify all of the different perspectives on derivatives that we're going to see going ahead. So I want you all to keep this in mind. We're only going to do one of those kinds of derivatives today, but for the rest of the next couple of weeks while we're doing multivariable derivatives, keep this in mind for all of them. Okay, all right. Okay, going to start with something called partial derivatives. I think a lot of y'all might have even seen partial derivatives before, and that's fine. I'm going to start off by saying a couple of good things about partial derivatives. Let's keep it positive. They're highly relatable. That's wonderful. Right? This is good news. They're going to look a lot like single variable derivatives in ways that we'll talk about in the next couple of minutes. Here's another really good thing. They are super easy to compute. We're going to see that momentarily. Okay. That's all good news. Now let me be a little negative. I think students are a little too attached to partial derivatives. A lot of students hang their hat on partial derivatives, and to me, this is what a derivative of a multivariable function is, and I know I haven't said what they are yet, but we will in a second. But a lot of students, once they see it, decide, okay, this must be the thing, and everything else I'll view from that point of view. And I do think that is a mistake. Okay, so I encourage you to view this as a first step. This is for lack of better ideas at the moment, I guess we'll try this, and yeah, it has some good features to it. But please, I have a different proposal for what I think should be your fundamental idea, your fundamental point of view on what is a multivariable derivative, and it's not this. So, for your consideration. Okay. Let me add one other good thing, right? So they're relatable, they're easily computable. Here's another third good thing that we're going to see as we go along. All of the other kinds of derivatives that we're going to see in this course, they can all be computed. They can all be sort of written in terms of and therefore computed with partial derivatives. So they are computationally sort of elemental. And that's nice, right? So it's a neat trick. If something's easy to compute and you can rewrite other things in terms of it, nice. Right? Okay. So you're going to see partial derivatives all over the place in the rest of this course, but it remains, I have a different answer to the question of what should be your fundamental actual point of view on what derivatives really are. Okay, I'm going to quit talking now and let's get to some actual details. So here's a multivariable function. I emphasize multivariable domain now. So this is truly, no kidding, multivariable. I'm going to start with just a single real value. We've already kind of seen in some sense what you do if you have multiple output values. If you have multiple output values, okay, deal with them one at a time, independently. It doesn't matter. Right? So I'm going to leave it single variable because why not? We'll fold that back in soon. So if I wanted to take a derivative of this thing, all I know about how to take derivatives at this point is how to take a derivative when there's a single input variable, yet it remains, at the moment, I have n input variables. And what I'm going to do is, honestly, kind of a cheap trick. With these n input variables, I'm going to hold all of the input variables constant. Just fix them, like staple them to the ground, right? They're not allowed to move for the purposes of what I'm about to do here. With that said, I'm going to leave one of them unfixed, right? And now if you think about it, if you have n input variables, but n minus 1 of those n variables are actually constants, are they really variables anymore? They're not really variables anymore, you know? Like if you have this thing called y, but you know y is actually equal to 2, then it's 2. It's not a variable. 2 is not a variable. You see what I'm saying? So what we end up with then is actually a single variable function. And with that in mind, we can just take the good old plain old Math 111L single variable derivative, where we take the difference between values of the function at some starting point and then add h. Look at that difference, divide by h, take the limit as h approaches 0. This is straight up Math 111L point of view on derivative of the single variable function that you get by just fix everything else. So cheap trick, right? By the way, let me be totally honest and criticize what I've done here. So really, despite all the buildup of how we're going to start doing multivariable derivatives today, I reduced the question to actually just doing a single variable derivative. And that's a very legitimate gripe, right? That's, weak That's a bad magic trick. If this were a magic trick, you'd be pretty disappointed, right? I'm doing the same thing that I've already done before. Okay. Nevertheless, this thing is going to turn out to be easily relatable to single variable derivatives. It's going to be really easy to compute. And all of these other kinds of derivatives are all going to relate back to these super relatable, easy to compute things. And so lame though it is, this is a very powerful trick as it's going to turn out, and that's going to reveal itself over a couple of weeks. Okay. All right, so this is the notation we use. We call it a partial derivative. No surprise, the variable, right, that you're doing this trick with, that variable that you're treating as a variable, the variable that you're taking the derivative with respect to, that variable, you put it as a kind of a differential looking thing in the denominator, just like the regular Leibniz notation for single variable derivatives. So I think that's very, very believable. The function that you're taking the derivative of, same deal, that function, yeah, you put a kind of a differential looking thing for it in the numerator. Very, very familiar kind of notation. The one kind of new thing is this little symbol here. I emphasize, this is very important, that is not a D. That's not a, I'm being fancy with my handwriting. It's not a D. Another common misunderstanding, a lot of students think that that's the lowercase Greek letter delta. It is not a delta. So it's not a D. And it is also not a delta. A delta kind of flops over to the right at the top. This is neither of those things. It's a new little symbol that doesn't get used before this point in math, typically. So anyway, you thought you were done in elementary school with your handwriting practice, but in fact, you got a new little character to learn how to make, and it's a humiliating experience to have to do this as a college student, for crying out loud. But you got to sit down with a piece of paper and decide, okay, how am I going to make it? Am I going to be a down and do the loop kind of person, or am I going to be a spiral outward kind of person? I'm a spiral outward kind of person, but I don't judge. Whatever y'all want to do, but you got to make sure that you can do this and make it look like it's supposed to look conveniently, efficiently. You don't want to have a little project every time you make that symbol. You want it to look good. You want to be able to do it quickly. And you want to be able to resist the temptation to, as you're doing this, to then go back down and make it a D. Because it's not a D. And it's very important that it not be a D. Okay. All right. So give yourself 2 minutes exercise with your new handwriting task. Okay. Right. So again, important that it's not a D. We are in fact taking a derivative of a multivariable function here. A derivative after a fashion, right? So in other words, specifically, this says, hey, yeah, I know it's kind of like a single variable derivative, but don't forget that there actually are other variables to this function that we are holding constant before we get to doing, yes, a kind of a standard single variable derivative. Okay, so not a D for that reason. Okay, so that's the definition. How do you compute these things? Good news. Super easy. These are the easiest derivatives to compute that I'm aware of, including single variable derivatives. I think these are easier to compute than single variable derivatives, which is, I know it's saying a lot. I mean, we have a lot of cute tricks with single variable derivatives. A lot of rules. We've got the chain rule, product rule, etc. Right? So let me show you how easy it is to do it. Don't forget our process. Our process is, if I want to take a partial derivative with respect to y, first step in the process is to recognize that we're holding all the other variables constant. Okay, so when I'm taking this y partial, I have to / get to and just feel like x and z are constants. I get to treat them like constants because they are constants. So x is a constant for the purposes of this calculation. Therefore, e to the x is a constant for the purposes of this calculation. X being a constant, Z being a constant, well, then cotangent of a bunch of stuff involving just X's and Z's, also constant. Right? So this looks like a great big ugly product, but in fact, for the purposes of a partial derivative with respect to y, this is constant times y squared. Right? All of this is constant. I have constant times y squared, and how do you take a now single variable derivative with respect to y of y squared? Oh, well, it's 2y. Well, times, of course, then don't forget, times that same constant. Yeah? So it's literally single variable derivatives with the added bonus that you get to basically ignore part of the function that you're looking at. It's a dream come true. Wouldn't that have been nice in a Calc 1 class when you're learning how to take derivatives if you could just look at part of the function that you're supposed to take a derivative of and say, you know what? This whole situation over here, I'm going to just call that a constant. Wouldn't that have been nice? Not only do we get to here, we have to. So, world's easiest derivatives to compute. And I'm going to whip through very quickly some other examples here. So this looks like a scary problem because we have a function to the power of a function. Right? By the way, do y'all know how to take, in general, if you have a function to the power of a function, do y'all know the trick for how to take the derivative? Importantly, when you have a function to the power of a function, you can't use the power rule or the generalized power rule because that requires the exponent to be a constant, right? So it's a hard problem. The answer, in general, is that you do this thing called logarithmic differentiation. My experience teaching this class is that quite a few students either never saw that or saw it once but it wasn't on the test and so they didn't study it, or by whatever reason don't know how to do logarithmic differentiation at this point in your math careers. And so given that that's the case, I have recorded a short video on my YouTube channel addressing how to do logarithmic differentiation. So if you're not ready to crush logarithmic differentiation problems, I think it's a good idea. I encourage you. It is something that we expect and assume that you know at this point. So give that little video a watch. It's like 20 minutes or something. And you can. Oh, y'all all know the following, I'm sure, but this is a recent discovery for me as an old guy. Did you know that on YouTube you can watch at like 1.5 speed? Yeah. That's awesome. It's super cool. I just did that with some of my own videos. I'm like, I can follow myself at 1.5 speed. It makes me sound weird, right? But hey, it gets the job done. And so anyway, it's a 20-minute video that you can watch in 13 minutes. So, cool. And if you dare, you can go double speed, but that gets a little weird. Okay, back to the problem at hand. Here we are taking a partial derivative with respect to x. So x and the parts of the expression that involve x are what I'm going to think of as a function, and all other variables, namely y in this case, I have to / get to treat as constants. And so this is not a logarithmic differentiation problem. This is u of x to the power of a constant. And I can straight up do the usual, bring the constant down, subtract 1, the usual deal, generalized power rule to compute its derivative. So easy. Okay. Likewise for the rest of these, let me... I'll just do one more real quick. So z being the variable here, notice that our exponent is z, but that means that y and x are constants, and so that means that this entire situation down here is a constant, and that means that we have a generalized exponential rule. We have a constant to the power of the variable we're taking the derivative with respect to. So you just use the generalized exponential rule. Which, by the way, reminder, Calc 2 is a prereq, Calc 1 is a prereq to that. I assume, therefore, that you remember how to do these kinds of derivatives, so make sure that you're good. I mean really proficiently, ready to crank them out, because that's going to happen, right, in this course. Really good at cranking out single variable derivatives. For example, this. Okay, real quick, one last one. Not everything is entirely trivial, but it's still a win. Taking the partial with respect to y here. What I end up with is actually kind of a product of two functions that still have y's in them. So yeah, it is nice that I get to view that as a constant, and it's nice that I get to view that as a constant, but I still do have a product of two, functions of y, so product rule. So I assume you know the product rule. This is how it works out in that case. Make sure you're good with that. Okay, so what have we got? We've got a definition, and we know how to compute them. What do we do with that, right? I mean, why? Who cares? Who cares that I can compute something that I wrote down a definition for? What does that buy me, right? Keep in mind, broad point, in general, it's good for something to be computable, but we only care if the thing that you're computing actually means something, right? It's got to be natural in some way. Physically, geometrically, right? It's got to relate to something in some way. So the next thing, very important, that we're going to talk about is how do you visualize? What do they mean geometrically, and do they have any physical, interpretation or context? So we'll start with geometrically. Geometric interpretations. Good news, we already have geometric interpretations of every step of our process. So all I have to do to figure out what partials mean geometrically is just go through that process and think geometrically at every step in the process. So it's a really easy process. Let's talk about how we do partials with respect to y, just as a first step. Partial with respect to y. So, when you take a partial with respect to y, that means x is going to be a constant. So we're fixing x. What's the geometric interpretation of fixing x? Well, fixing x means you're setting x equal to a constant value, which effectively means that you're focusing your attention on this plane, whose equation is x equals a constant. Right, so that first step, we have a geometric interpretation of it. And now if we're looking at a graph of our function, let's see here, if you're looking at here's our original function of x and y, and there's its graph. Focusing our attention on this plane means that we are doing a cross-section. So we're looking at this cross-section of that graph. That's very geometrically natural as our first part of our partial derivative process. Okay, what's the next thing that we do if we're taking a partial with respect to y? After we fix the other variable x, the next thing that we do, having fixed x, here it is, by the way, here's our cross-section that we get from fixing x. Next, we take the single variable derivative with respect to the variable y, right? We do the actual y derivative of this function. So, keep in mind, y is that variable. I'm going to take the derivative with respect to y. Flashback to Calc 1, what does it mean geometrically to the graph if you're taking a derivative? It means slope of the tangent line, right? So it means that we're going to look at this tangent line here, the tangent line to the cross-section, and think about its slope. So there you go. That's the geometric interpretation of a partial derivative with respect to y. Partial with respect to y is the slope of the tangent line to the graph of the multivariable function, but specifically the tangent line that's in the y direction. In the y direction, of course, because you're holding x constant. So let the record show a surface actually has lots of tangent lines, right? There's a bazillion tangent lines that go sort of, if you will, kind of loop around and go in all sorts of different directions. They're all tangent to the surface. You might even say there's an entire plane of lines tangent to the surface, right? The partial with respect to y is the slope of the one that's in the y direction. Okay. So, makes loads of sense. Now, here's an exercise. I want everyone to do the following. Think it through for what does a partial derivative with respect to x mean? If you want to do a partial derivative with respect to x, what does that look like and why? Again, think through the process. Now, by analogy, you can guess the correct answer. Yeah, sure. It's the slope of the tangent line to the graph of the function in the x direction. No surprise on what the answer is, but I think it's a valuable exercise to think through that process by analogy to what we just did. Okay, so we've actually got a lot done here. We made a definition of a new kind of a derivative. We've seen that it's supercomputable, and it means something geometrically natural. That's awesome. So we've done a little bit of multivariable calculus. I mean, kind of, sort of. We did some multivariable calculus by kind of reducing multivariable calculus to single variable calculus. So a little lame, I confess. But nevertheless, it's multivariable calculus. Okay. Now, shortcoming of this interpretation. It relies critically on the assumption that we are looking initially at the graph of the function. Right, where you make the domain sort of down here, the independent variables, and then you have your output variable, z, right, being height that tells you how far to go up, at each point, input point in the domain. So this is a very specific geometric construction, and this interpretation only makes sense for that one construction. So given that we've seen that graphs are a very limited tool in understanding multivariable functions, right? I mean, you can't even draw them pretty regularly, right? We need to think about, okay, well, how do I, what does a partial derivative mean? How do I think about it if we're looking at level sets or something like that? Okay, so I'm going to draw some pictures about that. Here's one that's more important than you might expect. But suppose we have a function from R3 to R1. Let the record show you cannot draw the graph, right? The graph would be a picture in 4 dimensions. Not on the table, can't do it. How do I think about a partial derivative here? Well, I'm going to revert back to the changes point of view. Remember, our idea of a derivative is it's something that relates input changes to output changes. So let's suppose we're at some point in the domain there that lands at a certain point in the target. So we're going to draw that point in the target that comes from this point in the domain. And what would it mean to say that we're going to hold all the variables constant except for y? In this context, it means that from that point, we are going to move in the y direction only. So we're going to move that way. Y is going to change. You might call that little displacement dy. Right? And derivatives relate input changes and output changes, so I want to relate that to, okay, when I make that change in y, correspondingly then, how much does the output change, dw? Now, I've confessed before, this is a very disappointing kind of a picture to draw. I can't see the shape of the function in any sense here. I've got one input and one output. It's extremely narrow point of view on what this function's doing. And yet, it is a picture, right? And there is something fundamentally natural about this point of view. I see graphically, in a sense, possibly a bad choice of words, ironically, a perspective on how input changes and output changes are the things that I'm looking at with this partial derivative, right? That's actually pretty nice. Okay. All right. So, anyway, it's a point of view. Here's another scenario. Let's suppose I'm looking at level sets. Now, this is another very respectable way to draw a picture that in some way helps you, in some sense, visualize a function. So, for example, if you have a function from R2 to R1, now I know we could draw the graph, but let's just suppose we aren't. Draw a bunch of level sets. All right. You can think of this, depending on your preference and what helps you see things, think of these as contour lines on the side of a mountain, perhaps, right? This picture helps you understand, in some sense, with the shape of the mountain, whose graph would be like a little model of the mountain. Right here, I have something two-dimensional that I can draw that still helps me visualize the mountain. what does partial derivative mean in this context? Well, it's a relationship between input changes and output changes. And let's talk about the partial with respect to x. The partial with respect to x says I'm moving in the x direction. And as I move in the x direction, I want to talk about the input changes and the output changes. Now, what's the story of this little arrow here? That little arrow says, well, if I move that far in the x direction, then I go up 200 feet on the side of the mountain. Which, that looks like a short distance, right? Over that seemingly pretty short distance, I go up 200 feet. That's a pretty steep mountain, right? I'm covering a lot. I mean, I went up 2 level sets. So let's say that's 200 feet. I'm seeing steepness in how close together the contour lines are as you go in that direction. Whereas, by comparison, let's think about the partial with respect to y. Well, you'd have to go that, come on, I can draw better than that. You'd have to go that far. That's a much greater distance in the y direction. I have to go that much greater distance to go up the same 200 feet in altitude. Well, that sounds like a much more pleasant climb, right? It's still a long way up, but instead of getting that long way up over a short distance, I get to get that long way up over a longer distance. So the geometric interpretation that you should take here of partial derivatives is that they are inversely related to how steep the mountain is, or to how fast is the function increasing in that direction. The closer together the lines are, in whichever direction you're looking at, the larger the value of the partial is. So different, let the record show, very different geometric interpretation than this slope of the tangent line business. Okay, and 2 seconds. And what it absolutely does not mean, and I've seen this happen a few times, some students just can't get it out of their head, the idea that that partial derivative isn't like maybe the slope of that tangent line. Oh, of course not. Not even close. Right? Not even close. So don't make that mistake. Yes?
So I was curious if the lines of like level set are parallel to the, like, for example, the y direction, that means the partial derivative of y is 0, right?
Yep, that's right. Gotcha. Yep, absolutely. Okay. So, moving along. Here's a neat application that we can do. It's going to concern the tangent plane of a function. In order to talk about tangent planes, I want to segue into that by analogy. We're going to start with tangent lines. Right, so I hope you all remember tangent lines from single variable calculus. Different ways to approach that topic. Here's the way I want to do it. I want to start with that I can define a function called the linear approximation. So the linear approximation to a function is a function L that has the following neat features. This function L has the same value as f that I'm trying to approximate, and it also has the same derivative as f that I'm trying to approximate. So in the sense of where and how fast, the linear approximation is the function that most closely mimics f. Right? And we can, you all have seen these pictures a million times, so I'm not going to rederive the formula. But if you have a function like this, let me make it a little curvier. You have a function like that, if that's your f, right, graph of f, of course. The linear approximation is a function that, it's at the same place that f is at the point we're looking at some point A. It's at the same place, and furthermore, it's going in the same direction as f. It's the closest linear ripoff of the function. Okay. All right, and for that reason, because it's got the same value and the same derivative, because it's a ripoff, this gives us a nice way to talk about the tangent line, the idea being that because the curve, highlighter mode, because the curve is the graph of f, right? The tangent line can just be the graph sorry, I got my things backwards. The tangent line, L, is the graph of, the tangent line is the graph of L. My wires crossed. Okay, so in other words, look, if L is doing a really good job of approximating F, then the graph of L is going to track the graph of F, and isn't that the idea of what we feel like a tangent line should be? It's a line that's following the curve. Well, the function L is following the function F, so that seems like a reasonable choice. Okay, so make sure to remember this point of view, and I remind you, I know I say this a lot, I think this is really important, please do make sure to distinguish between the function and the graph of the function, right? So f is a function, this curve is the graph of the function. Likewise, L is a function, this green line here is the graph of that function. Okay. Alrighty. Now, this formula for the linear approximation, where do we get that from? How do we do it? Again, there's a million different points of view you can take, and I'm just going to tell you the one that I like. I think it's best to just confirm directly that this function has the same value as f at a, and it has the same derivative as f at a. In other words, if you plug in x equals a, L of a is equal to f of a. If you compute L prime and then compute L prime of a and compare that to f prime of a, yeah, those match up too. So, little exercise, make sure that you can do that. Make sure that you can, in fact, confirm that this L has the same value and the same derivative as f at the point A. There's a couple little detail devils that you got to make sure that you are clear on before you do that. Okay. All right, so with that context, I hope this comes as no surprise. We're going to look at this function here. This function that I'm going to call the linear approximation. And I know you've never seen this before. That's fine, no problem. Why do I call this the linear approximation? Well, because it does the same thing that this L does. It's got the same value as f at some point in its domain, and it's got the same derivatives, plural now, as f. And this is another assignment that I want you to take, which is confirm that this function here has the same value as f when you plug in the point a comma b. Make sure that you can do that. And by the way, it'll be a very, the way that algebra works out is just like the way this algebra works out. So that's why this is a good warm-up problem, right? And not only does this have the same value as f at a comma b, it also has the same partials as f at the point a comma b. Now there's two of them, right? So this has got the same x partial as f, and it's got the same y partial as f. So this is the linear approximation in the sense that this is the function that, in a linear sense anyway, most closely approximates this function f around that point. So straight up rip off of this idea extended to a multivariable setting. And then just like we did here, we look at the graph of the linear approximation. Think of that as the tangent line to the graph of the function we were looking at in the first place. We're going to do the same thing here and talk about how, well, the graph of the linear approximation, green. The graph of the linear approximation is going to be a plane. If I were to look at the graph of f, right, well, this green graph and the blue graph, these are graphs of functions that, well, they have the same value at the point in question, so that means that they go through the same point. And they have the same partial derivatives. That means that the slopes of the cross sections in the x and y directions are the same. And I think it's a pretty easy appeal. You should expect this plane to be a tangent plane to the surface that we're looking at. It's got the same, it's in the same place, and it's got the same kind of slopes in both of the directions that you might want. So that's the name tangent plane. Okay. All right. So great little calculation. Again, I think this is important. Everybody should do this. Make sure you do the calculation. Confirm that this does have the same value and the same partials. It shouldn't take you long. But if you get stuck on it and don't know how to do it, you should absolutely come and get help on that. Ask a classmate. Ask me. By the way, quick reminder, you are all officially invited to the office hours of all of the instructors of the course for this semester. Asterisk. Section 6 and 7 are weird this semester. That they're doing a different thing, so you can't go to there. But sections 1 through 5, you're welcome to all those office hours. So capitalize on that. Okay. So so that was a function of two variables. What if you have more than two input variables? What if you have n input variables? Now I can't draw the graph. So I could, if I were to come up with a notion of linear approximation, I'm not going to be able to visualize. If I say, the graph of this linear approximation, it's in n plus one dimensional space. I can't draw that picture, right? But notice that you can still talk about the linear approximation itself, right? This function, I claim this is the formula for it, that has the same value as f at the point A, and that has all of the same partial derivatives as f at A. In other words, the function, which if I could visualize the graph plane-like thing, whatever that is, up in Rn plus 1, if I could visualize it, then it would have all the same slopes in all the given directions. And so it would be reasonable to call it the tangent, plane whatever for the function. Okay. All right. Okay, how are we doing? Is everybody on board? All right. Okay, let's talk about higher order partials. This is really just a kind of an easy observation that, if we have a multivariable function, I can take a couple of partials of it. I could take the x partial, I could take the y partial. Notice that the function f, being a function of x and y, I can talk about its x and y partials. That's why I can do this, right? But now check this out. The x partial, also a function of x and y. The fact that it's a partial of something else, okay, whatever. I don't really care about its origin story, right? This is a function of x and y, and because of that, I can talk about its partials with respect to x and y, right? And so I can talk about its x partial, and I can talk about its y partial. This y partial is a function of x and y, and again, ignoring the origin story. Being a function of x and y, I can talk about its x partial, and I can talk about its y partial. So just an observation that, knock yourself out. If you want to take more than one derivative, cool, go ahead. It's fine. Nothing's stopping you. Okay. Now, how to calculate them? All the same business, right? This is a function of x and y. It's subject to all the same rules. Yeah.
Wait, so whichever one you calculate second?
Let's talk about notation. Thank you for that. Right. So this is the notation that I've showed you for partial derivatives. This is an alternative notation that has some nice features to it in some occasions, where you just make it a subscript. This is what you might call the attempt to recover Newton notation. Right. So remember, in single variable calculus, you can talk about df, dx, or you can talk about f prime. And so in the same way that this kind of adapts to partial derivatives to become that notation, this thing kind of adapts, if you will, to become that notation. And it's tempting to say, well, why don't we just call it f prime? Well, the problem is that's a little sort of cheat that we can get away with in single variable calculus because there is only one variable. I don't have to indicate which variable I'm taking a derivative with respect to if there is, in fact, only one. It's unambiguous. Right? But now that there's multiple variables, if I were to say f prime here, you'd be like, what, do you mean x partial? Do you mean y partial? It's not clear. right? So we just make it a subscript, and the variable in the subscript is which partial you're taking with respect to. Okay. That said, then let's think about, when you do the next partials, the x partial. If you want to take a x partial of it, then you might write it like this. And to the question that was asked, I would write this as fxx. And then you also might take this function fx. You might want to take its y partial, right? And then this thing that you get, I would write as fxy. Because you're doing the x partial first, so you want that closest to the f. That's sort of acting on f first, so it should be closest to f. And then after that, you're doing the y partial of it. Okay. Yeah. Yes?
So then if you're ever taking derivatives or whatever, how do you write that in this?
If you what now?
If you're taking another derivative, do you do f prime of x with respect to x?
You don't do primes, right? So the subscript is itself. The subscript says I'm taking a derivative with respect to that variable. And then here I'm taking a derivative with respect to that variable. Maybe I didn't understand your question. I'm sorry.
So would you never take another derivative?
Oh, so you mean a third partial?
Yeah.
Sure. Yeah. Then you just keep writing subscripts.
Oh, after.
Yeah, just go as far as you want to go, right? For whatever reason, yeah. Let's talk about the Leibniz notation. This, you'll notice that's kind of what you get if you take the partial with respect to x and then take the partial of that with respect to x. So, if you will, this first x partial is there, and then you're taking a x partial of that. And then this is just notation, and it's a little lame, and I apologize, but there's two partial symbols right next to each other, and so we write, it's as if they're squared. They're not squared. It's not, we're not multiplying partial times partial. That's not a thing, right? But they're right next to each other, and that's just what people write, and it's a little grating, but it's extremely standard, so embrace it. Right? And then likewise down here, these x partials, it's as if they're not being multiplied by each other. There is no single thing called partial x. That's not a thing. Right? So it is not a thing, then you can't talk about what the thing does when you multiply it by itself, because that's just not happening at all. But notationally, this is how we write it. So again, embrace, uncomfortable though it is. Hey, by the way, quick observation to notice, the y partial of the x partial in this case happened to work out to be exactly the same as the x partial of the y partial. What are the odds? Weird. Turns out this is not a coincidence. This, I'm going to say, usually happens. Now there's an asterisk. You need for all of the second order partials to be continuous functions. It's a big deal, right? If that condition is not met, then you cannot assume that the mixed partials will equal to each other. But since very often the functions we're looking at are just nice, right? Polynomials, for example, are infinitely nice, right? Most of the functions you deal with in life are nice. Right? So, like I say, usually this will be the case. But don't forget there is that condition on it. Okay. Next question. What do these look like? The first part of the story that I think we can finish in the next few seconds here is actually a pretty easy story here. What do the second partials look like? Well, the non-mixed second partials, like let's take what does fyy look like? For both of the partials that we're taking there, we're fixing x. So x is constant for both of those partial derivatives. That means we're just taking literally a second partial with respect to y of this cross-section. And we already know what second partial means for a curve. Second partial means concavity. Right? So this curve is concave up, and that means that this second partial with respect to y is greater than 0. Or said differently, if you see that cross-section is concave up, that tells you that the second partial with respect to y is greater than 0. Analogous for the x, notice if you hold y constant and look at that, again, we have a Pringle function here, so this cross-section being concave down, that's the evidence that the x partial is negative. X second partial, that is. Okay, so easy interpretations in those cases. Now there is something that we have not addressed. I have not addressed what do the mixed second partials look like, and we don't have time for that. We're out of time for today, but we'll pick up there on Monday. So see y'all later. Have a good one.